I can actually turn the video off for this. I can. I will in a second. All right. So yesterday, and you can see my pencil bag now. That's better. Will the great tutors, Xavier, that is actually a very good question. I'm writing it down. I think though, Xavier, I'm going to be honest. I think from the email I got, I think there's only 4 people who are actually not going to be teaching in their own classrooms. But I will get back to you. I will send a message today and ask. Okay. The problem is, Xavier, we cannot actually have a whole meeting with you guys. You're too big. There's more than 50 of you. Okay. Is my camera flipped? No. Can you just not see that? Am I upside down? You're welcome, Xavier. Am I upside down, Luca? Because that would be weird. I'm just covering my second camera because it's on my iPad. Oh, no, you can. No, that's from my iPad, sweetie. That's from my iPad. I'm like, no, that's my iPad camera. Yeah, I know, I'm on 2 cameras, guys. Because I'm clever. I don't want you to see my face in 2 places. That's just scary for all of you. Okay, so you've seen, once I share my screen, you won't see my ceiling fan anymore. Okay, here we go. So, yesterday, let's get back to the work. Yesterday, you'll see one or the other, I think. We were talking about the emission spectrum, okay, and we got to the end of that with the line emission, and we spoke about how it's about the fact that the electrons jump, and when they jump, so they gain electrons, gain energy, and then they jump, and then once they jump, they give off energy, okay? And that gives us the line emission spectrum, which is when we see a streak of light, a color. So we see black, and then we get the color, okay? And I haven't forgotten about the activity I gave you. We'll do that in a second. So the second one we can get is an atomic absorption spectrum, okay? Now, what this means is this is the opposite of what we did yesterday. So yesterday we spoke about how the electrons absorb a certain amount of energy and then give that energy off, and we see that as light, certain colors. This works the opposite way around. So with the gas, so now what happens is we have hydrogen gas, we have a white light source, okay, which passes through the hydrogen gas, goes through a slit. This allows for diffraction. But what I want you to look at, okay, Isabella, let me just finish my thoughts and I'll come back to you, okay? What I want you to see here is that we get a whole bunch of colors, and then there's lines where we don't have color, okay? Now, Isabel, it's not a dumb question. An emission spectrum, the electromagnetic spectrum is all electromagnetic radiation. So it's radio waves, microwaves, infrared, the visible light, ultraviolet, X-rays, gamma rays, etc. Okay? An emission spectrum, okay, is a spectrum, is part of the light spectrum where we only seeing parts of it. So an emission spectrum is just a special part where we take part of the electromagnetic spectrum. Does that help? They're not really two different things. It's just whether we see it continuously or whether we see parts of it, basically. Okay. You're welcome, sweet pea. So the line emission gave us streaks with colors. Here we see most of the colors, but some aren't there. Okay. So it's wavelengths. The reason for this is the opposites now happening, is that the electrons absorb some energy, so the atoms allow most of the energy that's going through it to go through and absorb the rest of the energy. So when that energy goes through that certain frequencies, it absorbs some of those frequencies and keeps them. By keeping them, they produce those black lines. Okay, and it's an absorption spectrum because I'm keeping those frequencies. I'm absorbing them. Okay, but it only happens when we pass white light through the gas. Okay, emission spectrums happen with hot gases. Okay. Absorption spectrums happen with cold. Okay. If the electron in a hydrogen atom absorbs that amount of energy, it'll make a transition. It's all the things we were talking about yesterday. They're not going to ask you a lot of detail here. Okay. Energy of a photon must exactly equation to the energy difference. That must be exactly equal. Well, that's nonsense. Must be exactly equal. We spoke about that yesterday as well. Okay. Certain energies will be okay. So only certain ones are absorbed. Now, hydrogen's absorption spectrum and line emission spectrum are the inverses of each other. And it's really hard because you guys don't do negatives. So you guys, because you work in a world with digital cameras, unless any of you do, you've never really come across the concept of a negative. So the negative is like the inverse of a photograph. So when you take photographs on film and you take it or you do it yourself, it's a real skill. The film comes out, but you can't. I just want to ask the comments if it's my network or does. It might be me, Electra. Am I glitching lots today? Are we having moments? Aha. Okay. This is not good. So, all right, guys, what we're going to do then is, I think the recording is better, but are we gonna be okay? No, Isabel, you do not need to, Isabella, you do not need to know the actual spectrum at all. Okay, so it's one they use often. But don't know. You don't need to be able to draw it. You don't need to be able to tell me how many lines it's got. None of that. Okay. This is something that people would look up in books anyway. So don't stress. No, it's definitely my network, guys. I can see it. Okay, I know what's going on. I'm going to fix this. So I'm going to hang up here so you won't be able to see my face. There we go. No, you weren't. I'd muted myself. Should I say that again? Can you hear me now? Oh my word. Okay. You know what, Gabby? Maybe that no, it's upside down. No, let's not do that. I don't want to do that. Okay, I'm back now. That was fun. Okay, sorry about that. I'm back. You should all be able to hear and see me now. See, yes, good. Gabby, maybe you were right about that free lesson. Not going to happen though. All right. So let's go back here because this is what we were talking about. All righty. So, Isabella, back to your question, which I think has now just gone, who knows what else happened. Anyway, you don't need to know the line and emission spectrum. All right. The specific one, you just need to know what they are. Okay, so you need to be able to identify one, but you don't need to know hydrogen specifically, that it's got the violet, the dark blue, the light blue, and then a bit of red. You don't need to know that, okay? What you guys do need to know is that they're the opposites of each other. So your emission spectrum and your absorption spectrum are the opposites. They're direct opposites. Okay. Okay, Isabel, it's all right. Isabella, what is with me today? Okay, it's Friday. Let's just be honest. Isabel, I did make a change here because it doesn't quite make sense. Okay, so energy of photon must be exactly equal to the energy difference of the two. All right. So remember, that is the energy given. So we spoke about this yesterday when we looked at the diagrams. This is just the statement going that if I look at how much energy the electron absorbs, okay, and if the electron wants to go up 3 energy levels, it must absorb 3 energy levels worth of energy. Okay, so the photon must have the right amount of energy for the electron to absorb it, basically. Okay, that's what we're trying to say there. We good? Does that make a little bit more sense? I'm not good first thing in the morning. We've just realized.
Okay, ma'am.
Yes.
I'm just gonna unmute because it's easier.
Absolutely.
So is that the energy of the photon? Is that when the electron's getting excited, or when it's coming down to another level? Level?
The energy of the photon is when it's getting excited. Okay, so this is for the energy that needs to be absorbed to get the absorption spectrum.
And then where it says to the energy difference between the two levels, is that when it's dropping?
Okay, for this one, whether it's dropping or being absorbed, it's the same amount of energy. Okay. So for an absorption spectrum, it absorbs the energy of that photon, so you don't see that color anymore. With an emission spectrum, it gives it off, and then you see that color when you see the spectrum.
Okay.
Thank you. You're welcome. Do you have a bird?
Yeah. It makes a lot of noise. I'm sorry.
No, I think
talking now as well.
That's so cute. I like it. Okay. Alrighty.
Thank you, ma'am.
You're welcome, Isabella. Okay. Guys, I really don't mind if I'm missing you just need to unmute yourself, again, Isabella. I really don't mind if you jump in because you're not sure how to write the question. Okay, especially now that I can't see you, basically. All right, so let's go back here. The fact is that these are opposites of each other. Now, I need you to see the question here. I have specifically there's no activity in the book that makes sense for this section, which is why I've gone to the revision and extension. Okay, the memo to that isn't in the teams yet. The activity in the textbook is really lame. So that's why I went to the revision and extension, because that's more like what you're going to get in exams. Okay. But before we get there, yesterday I asked you to do question 1 and 2 of activity form, page 333. So let's go to that, because I need to make sure that we got those, because those are the ones where we're looking at these are questions. Okay, there is a worksheet. Okay, let me just give that. I'll give it to you in a second. There is a worksheet that I need you to do a couple of questions of, that we'll go through together. Okay, so looking at this one, I gave you some hints yesterday that those were the equations you're going to use. And here, it really is about writing down what you know, because when you write down what you know, it makes it easier to make a decision about where you need to go, what the question's asking you, okay? So they tell us that the work function of copper is 6,656 times 10 to the minus 19. First thing I'm going to do is I'm going to give myself some lines to write on. But, so over here, so this is question 1.1, all right? And they tell me that my work function is 6,656 times 10 to the minus 19 joules, okay? So we know that's the work function. Then they say minimum frequency. Minimum frequency is threshold. It's FO. They want FO. And state whether this radiation is visible. Okay, now that's an unusual question to ask. They wouldn't ask you that without a spectrum for you. Okay, they don't expect you to know the electromagnetic spectrum values. That's not expected at all. So WO equals HFO. We know W. I really don't like that first 6. Can you tell? So 656 times 10 to the minus 19. 6,63 times 10 to the minus 34. Remember, that is a constant. So that's always given to you. And we want FO. So it's just simply looking for that. Okay. Now, in terms of whether this is visible, I'm going to be honest, I would have to look that up. And I didn't even answer that question because I don't really care. So I'm just going to look it up in one of my other textbooks quickly. No, that one's not going to help me. Never mind. It doesn't matter. Okay, they're not going to ask you whether it's in the visible range. You don't have to know those frequencies and wavelengths. Grade 12s, please don't go and spend time learning them. You don't need to know them. Okay, so that's question 1.1. 1.2. Maximum.
Ma'am,
Yes.
is it negative or is that an equal sign?
That's an equal sign, Gabby.
Okay, I'm just making sure.
You know what? Today you need to. It's fine. That's an equal sign, sweet pea.
Okay, thank you, ma'am.
You're welcome. Somebody's hasn't fallen asleep yet. Okay, so now, okay, they want the maximum energy of the electrons. Energy means EK when the surface is exposed to the radiation of 1,2. So that's F. All right, that's F. This is why they've done this. Okay, they've led you a little bit because they asked you to work out Electro, can I write it neatly and post it on Teams? It's already written neatly and posted on Teams. Just so you know. How rude. I understand. I know this isn't always the neatest. It is. I think I've posted these memos. I can't remember, sweetie. Just have a look. Okay. If not, I will make sure it's on today. I understand that this doesn't always help you. Okay. So, what do we know now? We're back here. Oops. 1.2. I know WO. We've just worked it out. We know that the frequency that we're working with is 1,2 times 10 to the 15. All right. We know that we know WO, they want Emax. That's what they're looking for. So, and I'm going to try write neatly for you, okay? I know it's because I write too fast. It's all right, Electra. I'm not offended, I promise, sweet pea. So, we know E, which is from the photon, is WO plus EK max. I really must write neater, so don't stress, sweetie. I don't know E. I have to work it out. So we remember that E equals HF. I'm not going to work WO out because I know what it is. So I'm going to leave that as WO and I'm going to leave that as EK max because that's what we're looking for. All right. Now, H is 6,63 times 10 to the minus 34. Frequency was 1,2 times 10 to the 15. All right. WO was given 6,656 times 10 to the minus 19 plus EK max. All right. So all we have to do is solve for EK. EK max is then equal to 1,30 times 10 to the minus 19 joules. Okay, so it's really not that bad. I think sometimes we try to make it harder than this is. The hardest thing about these questions is being able to recognize what they're asking and not work out more than I need. Okay, sometimes you tend to go a little too far with them. So in other words, what I'm saying to you is for a question like this, for some reason, you'll go and try and work out the velocity of the electron when I didn't ask for it. Okay, so just be careful. Yes? I hear somebody. Yes?
It's me. Do we have to write that first line where it says E equals the work function, or can we just do the second line?
Second line's fine.
Okay,
Second
cool.
line's perfect. They'll You're welcome, Kyra. Oh, look. Hello, Kyra. That was so nice. I can see you talking to me. I remember all of you. When it comes to the equation, because there's so many forms of this equation, they'll accept it. All right. So the second one's fine. Absolutely fine. Question 2. Now they go, there we go. Let's take out all that other rubbish so now I can do this. So once again, the work function for a piece of zinc now is 5,76. So they've given you WO. If it is illuminated, that means we just shine light on it. of ultraviolet radiation with wavelength of 253 nanometers. They then want to know what the maximum energy is. They want to know what EK is. Here they've been maybe a little mean because they're not giving you frequency this time. So if we do it the way we do all of these, and I think this is why you need to get used to writing lists. I know you don't like them, okay? But it helps. So they told me that WO is 5,76 times 10 to the minus 19 joules. They then told me that the wavelength that we're using is 253 nanometers. But remember, we can't use it in nanometers. We have to change it to meters. So we're just going to times by 10 to the minus 9.
Ma'am,
Yes.
sorry, while we're on this wavelength, I remember with one of
Yes.
the questions in the other activities, they asked us to work out wavelength, but then in the solutions, the answer was in nanometers. Should our answer be in meters or nanometers?
Meters.
Always.
Meters. Yeah.
Okay,
Unless they
thank you.
specifically ask you. Okay. So they might go give your answer in nanometers, but if they don't, meters is fine. That's the SI unit. Okay.
Thank you.
You're welcome. So now what they want is EK max. That's what they're looking for. So I'm going to use the equation that we used last time. Okay. But the difference here is I can't use HF because for E, because I don't know F. So we're going to have to use this version of the equation. Remember, that's one of the other versions. I know WO and I want EK max. So once again, this is about substitution. So 6,63 times 10 to the minus 34. And remember, C is a constant. Okay. 3 times 10 to the 8. We know the wavelength that was given to us. We know WO that was also given to us. We just need to solve for EK. So this is a maths problem, okay? And what we get is 2,10 times 10 to the minus 19. And it's tiny, which I expected. But now, if you guys tried this, I'm hoping you're going to see that for the next question where they ask you for the velocity, you're going to get a ridiculously big number. And you must, okay? Because the next question says, what is the velocity of the electron? How fast is this electron going? Here, guys, this is very, very important. The mass of an electron is given to you. All right, it's given to you on your information sheet. And it's 9,11 times 10 to the minus 31 kilograms. It is ridiculously tiny, but we expect that. So even though this value is very small, when I put it into the equation to find for EK, to find velocity, it's all going to work itself out. So now watch, okay? EK equals a half mv squared. We know EK. We've got the half. It says 9,11 times 10 to the minus 31. Biggest mistake you're going to make here is you're going to forget to square root your answer here. So you're going to solve for v squared, and then you're going to forget to square root it. Please don't forget to square root it, but this is what we get. (6,79) times 10 to the 5. I am very, very happy with that answer. That's very normal. there is a value that it cannot go above. Okay, so when you get this answer, you need to keep in the back of your mind that it cannot be bigger than this, because 3 times 10 to the 8 is the speed of light. Your electron's going to go close to it, all right, but it will not get there. You will get ones where that number can be as big as a 6 or a 7. If you're getting close to 3 times 10 to the 8, re-look at things. Okay, go look at your maths. Go look at that. You haven't made a mistake somewhere from a maths point of view, because that's where you're going to make the mistake on that one. All right, so just be careful with that one for me, because there's definitely issues with that one. Okay, so now the
Ma'am,
next, yes,
why can it not be bigger than 3 times 10 to the 8?
because that's the speed of light. And as far as we know, nothing can go faster than the speed of light. Okay, and through experimentation, they haven't got anywhere where they haven't done any experiments where they found that the electrons go faster than that. And as far as we know, nothing can go faster than that.
Okay, thank you.
Okay, you're welcome. Look, the speed of light is one of those things when you watch sci-fi movies and stuff, and they go, oh, we're gonna go at warp whatever, or go through a wormhole and all sorts of things. They're all saying they're going faster than the speed of light. But at the moment, it's not possible. But you never know. Maybe we will live in a galaxy far, far away with Jedis. And I've had a Star Wars marathon recently. Let's just move on. So I then asked you, well, in the notes, it said you needed to do the revision and extension parts of the notes. Now, unfortunately, because of the way I took the screenshots, it's come out a little bit funny. So there's the first question. Okay. And that's from I'll tell you now, page 338. Okay. So this is on page 338. And we're going to go through these now, because I think it's quite important that we see how they work. Okay. Electra, for you, I haven't actually written this out neatly yet, but I will. I promise. Okay. I do know that when I write on here, things get a little messy, and I write all over the place, and I do sometimes feel sorry for you guys. Not often, but a little bit from time to time. Anyway, so let's look at question 2. All right, and we are almost done for today. I'm not going to carry on for too much longer, because I know you want to move on, and I'm going to see you on Monday. I'm so excited. It's very sad. Anyway, so the ionization energy of hydrogen. Now, I need to put this in context for you. In grade 10, way back then, you did ionization energy. Now, I know you haven't heard that term for a long time. Ionization energy is the energy required to remove an electron. Yes, it's in your textbooks, page 338, Savannah. To remove an electron from an atom in a gaseous state. So basically, ionization energy is telling you how much energy I need to get the electron to move. Okay. Now, when they say, what is the speed of the slowest electron that can ionize a hydrogen atom when it collides with it, is they're going, this would then need to be the energy that it has. This would have to be the kinetic energy. So they're saying, what would this be? So if we look back here and we go, okay, what they're telling me, no, that paper's just silly, it's too small. What they're telling me is this, is if my EK, all right, for what they've given me is, let's have a look, it's 2,2. Oh, no, wrong one. 2,2 times 10 to the minus 18 joules. How fast will it go? Well, we're looking at electrons. So the mass is 9,11 times 10 to the minus 31, okay, kilograms. All you have to do is solve for V. That's what they're telling you here, okay? So EK equals a half mv squared. Half 9,11 times 10 to the minus 31 v squared. So V 2,2 times 10 to the 6 meters per second. Faster than the last electrons, but that's because it's coming out of hydrogen. Hydrogen is quite happy to lose its electrons, actually. All right. The next question says, what is the longest wavelength of electromagnetic radiation that can produce ionization in hydrogen? This is the difference in the question, okay? What they're saying to you is I need to have a photon that has an energy of 2,2 times 10 to the minus 18, and I want to know what is the wavelength of the wave that would be associated with it. That's what they're asking me this time. So now I'm going to use E equals HC over lambda. Straightforward substitution. Okay, 6,63 times 10 to the minus 34. And I need to move this over because I've run out of space. 3 times 10 to the 8. And we're going to solve for lambda. Oopsie, didn't want that. And this one. It's quite a small wave. Okay. This is about reading the question and just putting it into the equations. Okay. So, and I think I'll just put it into the chat as well, because I think you're all going to forget what I'm about to tell you. I'd like you to do question 3 on page 338. I'll do a proper screenshot of it and give it and put it into the chat for you, because it's gone all funny on my notes. But what I'd also like you to try on the worksheet. Okay, so the worksheet is there, it's in your notes. So in the worksheet, I'd like you to do or try question 1, question 3, question 11, and question 12. Okay, I will go through those like we've done before. So I'll go through them like we're doing a normal, like we do in class. So I'll go through it and make sure you're all on the right track and make sure you all sort of understand what was going on. Okay. I do realize that for some of you, I could do it 17 times. Please try. Guys, I know it's the weekend, and I also understand that it's your last weekend before we go back to school, and it's been quite hectic. So, you know, I also need you to have some downtime for me, guys. Okay? Very, very important. You can't just work the whole time. All right. So, on that note, I am done for the day. Okay?